In the previous lecture, we have looked at various types of systems. Among these systems, the most popular one are the one that are linear as well as time invariant both. So this special class of systems that are both linear as well as time invariant are called as LTI systems. Now these systems are very popular in signals and systems due to their simplicity, and also these systems are very useful in modeling various physical processes. So we shall be analyzing LTI systems all during this course. Now let's look at the LTI systems in more detail in this module. Now, as I said, a system is an LTI system if it is both linear as well as time invariant. So let's consider a system that is an LTI system. So it is both linear as well as time invariant. And let's suppose that we have applied some signal to this system. So the input to this system, let's suppose we have applied very basic signal that we have learned in the previous module. Let that be del of n. This is an impulse being applied at the input. And let's suppose we have obtained certain output as a response to this impulse. Let that output be indicated with, say, h of n. So what is h of n? H of n is simply the response of the LTI system when impulse is given as the input. Therefore, this is also called as impulse response of the system. Now, as we have the system both linear as well as time invariant, let's impose those properties here. Now we have del of n being applied results in the output as h of n. Now as the system is time invariant, if we delay the input, say by k amount, it should result in an equivalent delay in the output, so it will result in h of n minus k. What is k? The k here is the shift or the amount of shift that we apply to the input. So the output must also get shifted by the same amount. Now this we have obtained by imposing the condition of time invariance. Because we know that the system is time invariant. Now similarly, we can apply the linearity condition here. So what does this linearity says? Linearity says that the system must be both additive as well as homogeneous. Let's impose the homogeneity condition first. Now say we have scaled the input by some amount, let that be x of k. What is x of k? X of k is simply a scalar at location k. So if we scale that impulse by a certain amount, let that be x of k, then the output must also get scaled by the same amount. So that is x of k multiplied by h of n minus k. How do we obtain this? This is obtained by taking into consideration what is called as homogeneity. Now let's impose the last property, that is additivity. We know that the system is linear as well as time invariant, so we have imposed the linearity property here. So in order to apply the linearity property, we have firstly imposed homogeneity, and now we are imposing what is called as additivity. Now the additivity property says that if we add two input signals and if we get some outputs, the outputs, the individual outputs must also be getting added. So let's suppose if we have multiple such inputs. So we have, say, summation of all such inputs. Let's say x of k into del of n minus k, the k varying from all the way from minus infinite to infinite. What does this mean? We have taken the linear combination or the summation of individual scaled and shifted version of the impulses. So that should result in also the summation of individual outputs. So that should result in summation of k running from minus infinite to infinite, x of k h of n minus k. How do we obtain this? We have obtained this by imposing the property of additivity. Now let's see what we have done. We have seen that we have some signal, let's say del of n, being applied to an LTI system. Say we have recorded some output, let that be h of n. Now, as the system is linear as well as time invariant, we have imposed those conditions one by one. First, we have imposed time invariance. So if we shift the input, we should get the shifted version of the output by the same amount of shift for, let's say, it is k. Next, we have applied the linearity. We have imposed the condition of linearity, and we know that linearity means both homogeneity and additivity. So homogeneity means if we scale the input, we must get the scaled output. So we have tried scaling the input by an amount, say x of k. Here x of k is a scalar. So we must expect the scaled version of the output. We have represented the same thing here. Now lastly, we have imposed the condition of what is called as additivity. So if we have multiple such linear combination of inputs, we must get multiple such linear combinations of outputs. So the linear combination of inputs must give you linear combinations of the output. That is what is a linear system does. Now if we observe this very closely, this thing here, this thing is nothing but, you can observe this, that this is simply a linear combination of scaled and shifted version of the impulses. And we already know what is this. What is this? This is x of n. We know that any signal x of n can be represented by the shifted and scaled version of the impulses. And on right hand side, what is that? Well, if this is x of n that we have applied, let this be the output signal, let that be y of n. So what is the interpretation here? If x of n, that is actually represented as the shifted and the scaled version of the impulses, if we apply x of n to an LTI system, we get the resultant output y of n as the linear combination of scaled and shifted versions of the impulse response, that is h. Interesting. So let me write this. The equation that we have obtained here is y of n equals to so if we apply x of n to an LTI system, we obtain y of n, that is the output, as summation x of k h of n minus k, where k is running from minus infinite to infinite. Now this thing here is called as a convolution sum. So this here is called as convolution. Convolution is again an English word. It simply says mixing. So let's interpret this equation here. What have we done? We have simply given the x of n as input to an LTI system, and we have found that the output of an LTI system is actually represented by scaled and shifted versions of the impulse response of that system. That means if we are aware of an impulse response of a system, we can calculate the output for any input. Strange. So if you have a system, LTI system, and if we are known of what is called as h of n, that is the impulse response of the system. If we know the impulse response of an LTI system, we can calculate the output for any input. So that's very strong claim that we are making here. So it's only the impulse response that matters. If we know the impulse response, that's all. You give any input, you can get the output if you know the impulse response of that system. Very important observation that we are making it here. And how do we obtain that output? We obtain that output by what is called as this formula that is called as a convolution sum. So convolution here is defined as y of n equals to the same thing here, k running from minus infinite to infinite, x of k h of n minus k. This is convolution sum here. Very important observation. Now you should note that this thing is true only for LTI system. So for an LTI system, let me write the conclusion here. The thing is, for an LTI system, if we know its impulse response, we can calculate output for any input. That means we just need to know the impulse response of the system. If that is known, we can determine the output of any input. So we don't need to check the output for each and every inputs. We just need to know the impulse response, and no matter what the input is, I can tell you the output by using what is called as this convolution sum. Now let's analyze this. What is this convolution sum? If we observe this equation very closely, we see that here this h of n here is the impulse response, x is the original signal, that is input signal, and y here is the output signal. So it simply specifies the relationship of input with the output. Now here write that. So x is the input, h is the impulse response, whereas y is the output. And if you observe this equation, we see that it is a relationship between the input as well as the impulse response. Now what is happening here? Let's analyze this equation. Let me write this equation once again, and this is the most important equation. Y of n, that is summation k running from minus infinite to infinite, x of k, h of n minus k. Now if we have h here, let's concentrate on h here. Now h here is an impulse response, whereas x is the input. Now here, this operation, what does it do is, it simply takes signal h, that is the impulse response. It simply flip that impulse. So you must note that both x and h here are functions of k, whereas n is simply the shift, the amount of shift here. So the h here is a function of k. We can treat h here as a function of k. If we do that, h is n minus k, and we know what is n minus k here. It can simply be represented as h of minus k plus n. I can do that because it's a simple rearrangement of this representation. So what does this mean? If we have this h, if we treat this h as a function of k, we are simply flipping this signal and shifting this signal. So if we flip this signal and then shift the signal by n amounts, we'll get the signal. So the overall interpretation of this signal is that if you have two signals, x and h, you consider h, you flip it, then shift it, multiply both of them, and then add it. In a sense, there are 4 different steps that are happening in this equation. So the first thing that is happening is the flipping. That is the negation operation here. Then shifting. Third is the multiplication, multiply, and final thing that we are doing here is to add all of this. You can see here that this h is, if it is being treated as a function of k, it is being flipped and shifted by amount of n. So it is flipping, shifting, multiplying, and adding. That will result in what is called as this convolution sum. Now let's take an example of this. Now I would like to demonstrate this sum, the convolution sum, with the help of animation. Now let x and h be 2 different signals. So let x be here, for example, let x be some signal like this. Kind of triangular signal. Very simple signal. Let this be x of n, and let another signal be let's say 1 over the same period. Now consider these two signals. Now this signal, what I'm saying as h of n. Now further we are going to look that this x and h doesn't matter as long as you try to flip either of these signals. Now let's consider this signal. Now here what is happening? We are simply trying to flip the signal, the second one, h. Now if you try to flip this signal, it is going to give you the same signal. The flipping here doesn't matter. Well, that won't be the case for every other h signal. The h can be different, but here in this case, after flipping h, it will remain the same. Now we need to shift this h all the way from minus infinite to infinite, and we need to multiply with this x. And as we go on multiplying, the resultant multiplication, we are going to add it all together. Now as this is for the continuous time case, it is very easy to verify that for the we have seen this for discrete time case. It is very easy to verify that similar kind of equation we can also obtain for the continuous time case. So for continuous time, we obtain the equation something like this: y of t equals to, instead of having summation, we'll have an integration from minus infinite to infinite x of tau h of t minus tau d tau. Now there is very close analogy between the continuous time and the discrete time case. For the discrete time, it was y of n equals to summation k equals to minus infinite to infinite x of k h of n minus k. Now we see that here in both of these scenarios, the concept remains the same. We take a signal, we flip it, shift it, multiply and add. All those four operations are available here. Now this example here, let's see this example with the help of animation. I'm considering the continuous time case, so let's consider the signal in continuous time as, say, we are taking the example something like this. Let's consider for continuous time case the signal be this and the other signal be like this. Now let's look at the animation. Now here we can see that we have considered this is the animation that is available on this website. You can see. Now here we have two signals. The first signal that we have here is this one, a triangular signal, that we represent that with h, and the x that we have here is this rectangular pulse. So here in this signal, I think I have exchanged this. So let this be, actually it doesn't matter, but still for this example, let me write that this is h of n, this is x of n. So this is h of t and x of t, just because this is continuous time case. So if you look at the animation here, this signal, a simple one, is X and the other one is H. So what does the convolution sum says? The convolution sum says that if we have this H, we simply flip it. That means we simply just twist or flip it. The negative side goes towards positive and the positive goes towards the negative, so the signal effectively remains the same. If we flip it, then we need to shift this, multiply and add. So let's look at the animation first and then try to explain this. If I'm starting this, you can see that here the signal here is sliding. We have flipped it, now we are shifting it. Now as we shift here, we multiply, and this is the result of multiplication here. After multiplication, we are simply adding them all together. So the result of adding is this one that you are seeing it here, y of t. Now y of t here is simply the integration of x of tau into h of t minus tau. So we have this h, that is this triangular signal, being flipped, shifted by amount of t, multiplied with x, and then integrated the area over the multiplication we are calculating. So I'll play this again. See here, so we have two signals. We have x, that is this pulse. We have h, that is this triangular signal. First we'll be flipping this triangular signal. So if we flip it, it remains the same in this example. Now we try to drag or shift this signal, just because in our formula we have this shift by an amount of t. So we need to shift it towards right, all the way from minus infinite to infinite, from left to right. Meanwhile, we also need to multiply both of the signal x and h, and we need to calculate the resultant sum or integration. So if I try to play this again, you can see that here after flipping the signal remains the same, and then we are dragging the signal all the way from left to right. We are multiplying meanwhile, and the multiplication will be observed here. See, the multiplication is increasing and then decreasing, and the resultant summation, or we can say the integration here, is such kind of signal. So the overlap, we can say the multiplication will give you the overlap. So the overlap increases and then decreases. So let's play it again once more. You can see here that as we drag the signal from left to right, because there is a shift of t, we multiply. Now as soon as it comes here, the axis matches, the multiplication here is significant, and then it vanishes, and then this point gives you the resultant integration here. This is the concept of convolution. So the convolution is simply the combination of four operations, that is flipping, shifting, multiplication and addition. It's simply this formula. We shall see more into this in the next module. Thank you.